Pluto, once classified as the ninth planet in our solar system, has since been reclassified as a dwarf planet. Despite this, it continues to captivate astronomers and scientists, especially after recent statements by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku, who have reignited interest in Pluto with a startling revelation. The distant dwarf planet may be on a collision course with Neptune. This potential cosmic event raises several important questions. How could such a collision even be possible? And what would its consequences be for our solar system? Could this be a rare cosmic phenomenon? Or is there more to this approaching infinite conflict? Pluto's orbit, unique and eccentric, has long been a subject of intrigue in the scientific community. Its orbit around the Sun is drastically different from those of the major planets. It takes 248 years to complete one orbit, meaning since its discovery in 1930, it hasn't even finished a full revolution. What makes its orbit even more unusual is its shape, which is highly elliptical compared to the nearly circular orbits of the other planets, and its inclination of 17 degrees to the plane of the ecliptic. These characteristics make Pluto's orbit more extreme and complicated. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years of each orbit, Pluto actually comes closer to the Sun than Neptune, which contradicts our expectations based on their relative positions in the solar system. This raises the natural question: why hasn't Pluto collided with Neptune yet? The answer lies in the gravitational interactions between Pluto and other planets, especially Neptune. When Pluto's orbit was first studied after its discovery, astronomers were puzzled by its strange path. Unlike other planets whose orbits are near the ecliptic plane, Pluto's path stands out due to its steep inclination and highly elliptical shape. As the investigation continued, it became clear that Pluto's orbit crosses Neptune's, and yet the two planets don't collide. This is because of the complex gravitational interactions, a scenario known as the three-body problem, which describes how the Sun, Pluto, and Neptune affect each other with their gravitational forces. Predicting their movements is like trying to calculate where they will be in the future based on where they are now and how they interact. To understand why Pluto and Neptune never collide, scientists turn to a concept called orbital resonance. This means that Pluto's orbit is in a unique rhythm with Neptune's. For every 2 orbits Pluto makes around the Sun, Neptune completes 3. This resonance helps maintain stability in their orbits, preventing any potential collisions. Additionally, Pluto's orbit is not perfectly aligned with Neptune's. The two planets are always at least 90 degrees apart when Pluto crosses Neptune's orbit. This spatial arrangement provides further protection from a collision. Moreover, Pluto's orbit is further stabilized by its libration, a phenomenon that involves a celestial object moving up and down through its orbital plane. This movement ensures that when Pluto approaches Neptune or other large planets, it is positioned above their orbital plane, adding an extra layer of safety. Another key factor in keeping Pluto's orbit stable is a gravitational phenomenon known as von Zeipel-Kailoff (VZK) oscillation. Named after 3 astronomers who studied celestial motions, the VZK oscillation describes how Pluto's orbit is influenced by the gravitational pull of Neptune, the Sun, and other large planets like Jupiter and Saturn. This oscillation helps to explain the seemingly erratic nature of Pluto's orbit, while ensuring that it remains stable over long timescales. While Pluto's orbit appears chaotic, these gravitational influences, especially from Neptune, Jupiter, and Saturn, work together to maintain stability. Even though Pluto's orbit is highly irregular, these forces help prevent the planet from veering off course or colliding with other bodies. This delicate balance is crucial for maintaining order in our solar system. Without it, objects like Pluto could either crash into other planets or be ejected from the solar system entirely, potentially causing a domino effect that would disrupt the entire solar system. In the case of Pluto, its orbit has been studied in great detail to understand how such a chaotic-seeming path can remain stable for billions of years. Recent computer simulations have shown that despite Pluto's orbital irregularities, the gravitational effects of Neptune, Jupiter, and Saturn work together to ensure that Pluto's path remains safe. These discoveries underscore the remarkable stability of our solar system. They show how even the most seemingly unstable orbits can find equilibrium through the complex interplay of gravitational forces. For Pluto, the idea of a potential collision with Neptune in the distant future seems unlikely due to the intricate mechanics that govern their paths. However, studying these interactions is crucial for understanding the dynamic nature of our solar system. The fascinating complexity of Pluto's orbit also highlights the importance of continued observation and research. As scientists develop new methods to simulate and understand orbital mechanics, we gain a deeper appreciation of how our solar system operates. Pluto's behavior is a striking example of how celestial bodies, despite their apparent randomness, can maintain stability through intricate gravitational relationships. This research not only sheds light on Pluto but also provides valuable insights into the broader dynamics of our universe. The complex mathematical models used to simulate the gravitational interactions between Pluto and other celestial bodies like Neptune allow astronomers to understand how even slight changes can significantly impact Pluto's orbit. These simulations have shown that, despite the presence of stabilizing factors like resonance and libration, Pluto's orbit remains unpredictable and chaotic over long periods. Small variations in Pluto's position or velocity can lead to vastly different orbital paths. Yet, even with this chaos, Pluto's orbit remains stable over billions of years, suggesting an underlying order within the apparent turbulence. Predicting long-term celestial events, especially those involving erratic orbits like Pluto's, is challenging due to the inherent unpredictability of these systems. Numerical models are powerful tools for forecasting the future behavior of celestial bodies, but they are highly sensitive to initial conditions and the complexity of the forces at play. Even the smallest errors or inaccuracies can lead to drastically different outcomes, making precise predictions a difficult task. The chaotic nature of planetary orbits, exemplified by Pluto, serves as a reminder of the dynamic and evolving nature of the universe. Although we've made significant strides in understanding space, cases like Pluto illustrate the limitations of our current knowledge. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of our solar system. It demonstrates how the positions of major planets can have widespread impacts on the stability and direction of smaller bodies within the system. This is why astrophysicists are increasingly concerned about the potential interaction between Pluto and Neptune. Despite the many forces that seem to prevent such an event, the possibility still exists, especially in light of new discoveries. Astrophysicist Neil deGrasse Tyson, known for his work in the reclassification of Pluto from a planet to a dwarf planet, offers a unique perspective on the mysteries of our solar system, particularly Pluto. He views the renaming not as a demotion but as an important shift in our understanding of the diverse bodies orbiting the Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation, recognizing that the complexity of orbits like Pluto's highlights the vast amount we still have to learn about space. His work emphasizes that as we uncover more about the universe, new questions arise, driving further exploration. Another renowned physicist, Michio Kaku, offers a different but complementary viewpoint on space's unpredictable forces. Known for his ability to connect complex scientific concepts with futuristic ideas, Kaku is an influential voice in discussions about celestial mechanics and the broader implications for humanity. He emphasizes the importance of continuous observation and advanced modeling to understand and predict potential cosmic events. Kaku sees the relationships between celestial bodies as crucial to understanding not just academic concepts but also the practical impacts these phenomena may have on humanity's future. The potential collision between Pluto and Neptune, for example, is not just a theoretical scenario but a reminder of the unpredictable and dynamic nature of space. Both Tyson and Kaku agree that space is an ever-changing realm, with our current knowledge still limited. Their work stresses the need for ongoing exploration and refinement of our models, highlighting the importance of understanding celestial mechanics as they are now while also predicting how they might evolve. The possibility of a Pluto-Neptune collision serves as a case study in the challenges and opportunities presented by space exploration. It underscores the need for robust scientific inquiry, advanced technology, and a willingness to adjust our understanding as new data becomes available. Despite the consensus that Pluto and Neptune's orbits will likely remain stable for the foreseeable future due to their orbital resonance and other gravitational influences, astronomers continue to monitor these bodies closely. While a direct collision remains highly improbable based on current models, the complexities and potential perturbations in their orbital elements necessitate ongoing observation to better understand their long-term behavior and any potential risks. The situation involving Pluto and Neptune, though largely theoretical and considered unlikely, reminds us of the importance of continuous research in space science. Advances in technology, including more advanced telescopes and computational models, will help astronomers refine their predictions and ensure we stay informed about the ever-evolving nature of our solar system. Tyson's perspective on Pluto's reclassification and Kaku's emphasis on the unpredictable nature of celestial mechanics both stress the need for adaptability in our understanding of the universe. The potential interaction between Pluto and Neptune, while unlikely, highlights the complex and interconnected nature of our solar system, reminding us of the vast unknowns that still await discovery. Through continuous exploration and observation, we aim to unravel these cosmic mysteries, ensuring that our knowledge keeps pace with the ever-evolving universe.